January 1941. Just before dawn. A small European town, still dark, still frozen under winter air. Beneath its cobbled streets, something waits. An unexploded aerial bomb lies buried several meters below ground, dropped weeks earlier during a night raid. Its steel casing is intact. Its delayed action fuse is not. Every vibration above, a passing truck, a closing door, even footsteps, sends faint tremors down to the device. The town has been evacuated, but not abandoned. Windows are shuttered. Clocks have stopped. Silence has become policy. In the center of this emptiness, a narrow shaft has been cut into the earth. Wooden supports creak as soil is removed by hand. No engines, no power tools, only shovels, lamps, and breath held too long. At the bottom of the shaft, an engineer kneels in the cold mud. He does not touch the bomb yet. He studies it. The fuse assembly is unfamiliar. The wiring does not match the diagrams issued weeks earlier. Somewhere inside, a mechanism is already armed, waiting for movement, corrosion, or time. If it detonates, the town above will disappear. The engineer reaches for his tools, and in doing so, steps into a story shaped not by explosions, but by precision. By the winter of 1941, the war in Europe had already changed its shape. What had begun as rapid ground campaigns in Poland and Western Europe had evolved into something colder, slower, and far more impersonal. The front lines were no longer only rivers and roads. They were cities, rail yards, residential districts. Entire populations had become part of the battlefield. Strategic bombing was no longer theoretical. It was doctrine. Germany's Luftwaffe had demonstrated its effectiveness during the Blitzkrieg of 1939 and 1940, using air power to dislocate defenses and terrorize civilian centers. Britain responded in kind. By 1940, RAF Bomber Command was reorganizing its mission towards sustained area bombing, targeting industrial capacity and morale. The air war no longer ended when the aircraft turned home. Its consequences remained embedded in the ground. Night after night, thousands of high-explosive bombs were dropped across Europe. Many detonated on impact, shattering streets and collapsing buildings. Others did not. These failures were not accidents. A significant percentage of aerial bombs were intentionally fitted with delayed action fuses. Some were set to explode minutes after impact, others hours. A smaller but far more dangerous class was designed to detonate days or even weeks later. The logic was strategic and cruelly efficient. Delayed explosions endangered rescue crews, blocked repair efforts, and forced evacuations long after the raid had ended. The psychological effect was as important as the physical damage. Civilians learned to fear not only the sound of aircraft, but the silence that followed. By late 1940, unexploded ordnance had become a crisis in Britain, France, Germany, and across occupied Europe. Entire neighborhoods were cordoned off around buried bombs. Rail lines were shut down. Factories stood idle. Cities already stretched by rationing and blackout regulations were now held hostage by devices hidden underground. The bombs themselves grew more complex as the war progressed. Anti-handling devices were introduced, mechanisms designed to detonate if the fuse was disturbed. Some are triggered by tilt, others by pressure release, a few by the very act of removing the fuse. Documentation lagged behind innovation. Engineers in the field often faced bomb designs they had never seen before. Manuals were outdated before they reached the front. Intelligence on enemy fuse types arrived slowly, sometimes too late. In many cases, the bomb that failed to explode immediately was more dangerous than one that had detonated on impact. Winter weather made the problem worse. Moisture seeped into fuse housings. Chemical delays became unstable. Corrosion altered tolerances inside mechanisms designed to operate within fractions of a second. A bomb buried in frozen ground might remain inert for weeks, then suddenly arm itself without warning. This was the environment facing towns like the one now evacuated above the engineer's head. The bomb beneath its streets was not an anomaly. It was the logical outcome of an air war that had expanded faster than the ability to control its consequences. And as the number of unexploded bombs increased, a new kind of battlefield role emerged, one that did not advance lines on a map, but fought time itself, one device at a time. The war created many kinds of soldiers. Some crossed borders, some flew above cities, others went down into the earth. As unexploded bombs accumulated beneath streets, factories, and rail yards, military planners were forced to confront a problem they had not fully anticipated. Clearing these devices was not optional. It was essential to survival, production, and morale. Yet the task required skills that conventional infantry training did not provide. Bomb disposal units were assembled quickly, often from engineers, electricians, miners, and civilian technicians already familiar with complex machinery. In Britain, the Royal Engineers became the backbone of organized bomb disposal. In occupied territories and across the continent, similar roles were filled by military engineers, fire brigades, and requisition specialists. Their training was brief, sometimes only days. Manuals existed, but they were incomplete by necessity. New fuse designs appeared faster than they could be cataloged. Anti-handling devices were often discovered only after they had killed someone. Procedures were written in blood, revised after each fatal mistake. By early 1941, the risks were well documented. Bomb disposal was among the most dangerous assignments in the war. Casualty rates were high, and survival often depended on experience rather than rank. Engineers learned to read subtle signs, the angle of a fuse, the smell of chemicals, the resistance of a screw, clues that could indicate whether a bomb was stable or moments from detonation. There were no second chances. Protective equipment was minimal. Heavy armor restricted movement and amplified shock waves. Many engineers worked in ordinary uniforms, sometimes without helmets, relying instead on distance and luck. In confined spaces underground, even that was unavailable, the psychological burden was constant. Each descent into a bomb shaft was undertaken with the knowledge that previous engineers had not returned. There was no rotation schedule that made the work safer. Fatigue accumulated. So did fear. Yet hesitation was more dangerous than calm. Engineers developed their own informal rules. Move slowly. Touch nothing twice. Assume the bomb is alive. It was within this environment that the engineer beneath the town found himself kneeling in the cold earth. He was not unique in his role. Thousands of others were performing similar work across Europe at the same time. What set his situation apart was not his courage, which was shared by many, but the specific problem in front of him. The bomb he faced did not match the diagrams issued by his command. Its fuse assembly showed signs of modification. The wiring layout suggested an anti-handling mechanism integrated into the delay system itself, a design intended to defeat standard removal procedures. To leave the bomb untouched was to condemn the town to indefinite evacuation. To attempt standard disarming risked immediate detonation. The engineer understood that the manuals would not save him. Only understanding the bomb completely would. And that realization marked the point where preparation ended and decision began. Before it was a technical problem, the bomb was a human one. The evacuated town above was not an abstract map reference. It was homes left unlocked in haste. Shops with goods still on shelves. Beds made, but unoccupied. Churches, schools, and narrow streets shaped by generations who had never imagined their survival might depend on a device buried beneath their feet. The engineer knew this, even if he did not see it. He had passed through the town during the evacuation. He had watched civilians carry what they could, leaving the rest behind. The silence that followed was not peace. It was suspension. Bomb disposal demanded emotional control more than bravery. Panic led to sudden movement. Sudden movement led to detonation. Engineers learned to compartmentalize fear, to reduce the situation to mechanisms and probabilities. Yet the knowledge of consequence never left. A miscalculation would not only end his life, it would erase the town above him. This understanding did not paralyze him. It focused him. The weight of responsibility narrowed his attention, forcing every thought toward precision. In that moment underground, there was no war beyond the bomb, and no future beyond the next minute. The human cost framed every decision he would make next. Aerial bombs of the early 1940s were deceptively simple from the outside. Steel cylinders filled with high explosive. Their lethality lay in their fuses. The bomb beneath the town was fitted with a delayed action fuse, likely chemical or mechanical in nature. These fuses were designed to trigger after impact using clockwork mechanisms, dissolving compounds, or pressure-driven pistons. Their purpose was disruption, not immediate destruction. What made this bomb different was its internal redundancy. The wiring suggested a secondary firing circuit, an anti-handling feature that bypassed the primary delay if interference was detected. Removal of the fuse could complete the circuit rather than break it. Standard procedure called for unscrewing the fuse assembly. In this case, that action might initiate detonation. Rewiring a bomb was not taught as doctrine. It was an act of last resort, based on intimate understanding of electrical pathways and firing trains. One incorrect assumption could energize the detonator. The engineer studied the bomb not as an enemy weapon, but as a system. Every wire had a purpose. Every connection implied intent. Understanding that intent was the only way forward. The tactical situation above ground was unforgiving. Evacuation could not be extended indefinitely. Winter conditions strained food supplies and shelter for displaced civilians. Rail lines near the town remained closed, delaying military logistics and industrial output. Command pressure mounted with each passing day. There was no opportunity to destroy the bomb in place. Detonation would collapse surrounding structures and trigger secondary damage across the town center. Flooding the shaft or burying the bomb deeper risked unpredictable movement. Time worked against every option except one. The engineer had limited tools, fading light, and incomplete information. He could not call for immediate reinforcement without delaying action further. The decision rested with him alone. All three angles, human, technological, tactical, converge at the same point. The bomb could not be removed. It could not be ignored. It could only be understood and altered. In wartime engineering, leadership was rarely visible. There were no formations underground, no shouted commands, no banners or insignia. Authority existed on paper, but reality belonged to the individual at the device. Once an engineer entered the shaft, he became the highest-ranking decision-maker present, regardless of his formal rank. Official doctrine emphasized procedure, but procedure assumed predictability. In bomb disposal, predictability was a luxury. Commanders understood this, even if they could not openly admit it. Reports from the field often contained careful language, action taken in exceptional circumstances, a phrase that concealed improvisation born of necessity. The engineer beneath the town was operating under general orders to render the bomb safe. How he achieved that was left deliberately vague. Success would be commended quietly. Failure would be recorded clinically. This was leadership stripped of ceremony. Responsibility without recognition. The decision to deviate from manuals carried consequences beyond personal risk. If the bomb detonated, questions would follow. Why standard procedures were not followed? Why unauthorized methods were attempted? Yet in that confined space, doctrine gave way to judgment. Leadership became an internal process, weighing outcomes, choosing between unacceptable risks. The bomb was not simply a product of industrial manufacturing. It was an argument made in steel and wire. German bomb designers, like their Allied counterparts, understood that bombs would be recovered, examined, and dismantled. Anti-handling devices were introduced not to increase blast radius, but to kill those who try to neutralize them. Some fuses incorporated tilt switches that completed a circuit when the bomb was moved. Others used mercury switches that flowed when disturbed. Still others were designed so that removal of the fuse released spring-loaded firing pins. The wiring visible to the engineer suggested intentional deception. What appeared to be a disarming path might actually be the trigger. The enemy's expectation was clear, that bomb disposal personnel would rely on habit and haste. By studying the wiring rather than touching it, the engineer was already countering that expectation. This was a contest not of force, but of understanding between the person who designed the bomb and the one now kneeling beside it. Bomb disposal forced a moral arithmetic unlike any other wartime role. Pilots risked their lives with crews. Infantry advanced as units. Engineers worked alone. The equation was brutally simple. One life beneath the ground weighed against thousands above it. The engineer did not frame his task in heroic terms. There was no room for abstraction. The choice was between acting and not acting, between intervention and paralysis. Rewiring the bomb would violate procedure, but inaction guaranteed prolonged danger. Removing the fuse followed doctrine, but risked immediate detonation. Each option carried consequences measured not in percentages, but in lives. The moral burden was not whether he would die, but whether others would. When all angles were considered, only one path remained, narrow, untested, and irreversible. The moment for analysis ended. The moment for action arrived. The descent into the shaft began before sunrise. The engineer moved slowly, lowering himself by ladder into the narrow space carved around the bomb. The walls were reinforced with timber, but the earth still pressed inward. Moisture clung to everything. Each rung creaked under his weight, a sound that carried too clearly in the confined space. At the bottom, the bomb lay partially exposed, its nose embedded in compacted soil. The casing showed no visible deformation. That alone was dangerous. Bombs that failed to detonate on impact often retained full structural integrity and full explosive potential. He did not touch it immediately. Instead, he adjusted the lamp, angling light across the fuse assembly. Shadows revealed detail. The fuse was seated tightly, suggesting it had not shifted during impact. That reduced the likelihood of a tilt-activated trigger, but did not eliminate it. Corrosion around the housing indicated prolonged exposure to moisture. The chemical delay, if present, might already have completed its cycle. Time was no longer theoretical. Using a thin probe, the engineer tested the soil around the fuse, clearing it grain by grain. He avoided vibration. He avoided pressure. Every movement was deliberate, rehearsed in his mind before it was executed by his hands. The wiring came into view. 2 insulated leads ran from the fuse toward the detonator. A third, thinner wire branched unexpectedly from the housing, a deviation from known designs. Its placement suggested it was not part of the primary firing chain. It was something else, an anti-handling circuit. Standard procedure would have been to withdraw, report the configuration, and wait for updated guidance. But guidance would take days. The town above could not wait days. The engineer traced the wire visually, following its path along the casing. It terminated at a secondary contact point near the detonator well. If energized, it would bypass the delay mechanism entirely. Removing the fuse would almost certainly complete that circuit. For several minutes, the engineer did nothing. In bomb disposal, stillness was not hesitation. It was calculation. He measured the spacing between contacts. He estimated resistance. He imagined current paths without ever closing a circuit. The conclusion formed slowly, then with absolute clarity. Disarming the bomb required not removal, but interruption. And interruption would require altering the bomb itself. The engineer reached for his cutting tool. The engineer paused before making the first cut. Rewiring a live bomb was not a procedure found in manuals. It was a theoretical solution discussed in fragments, in after-action reports, in quiet conversations between engineers who had survived long enough to compare mistakes. It depended on certainty, and certainty was rare underground. He began by stabilizing the fuse housing, packing damp soil carefully around its base to prevent movement. Even the act of cutting could transmit vibration. The lamp was repositioned again, closer now, illuminating the exposed wiring until every strand was visible. The thin secondary wire was his focus. Rather than cutting it outright, he exposed a short section of insulation using the tip of his knife, slow and controlled. He did not pull. He did not twist. The goal was access, not separation. The engineer understood that detonation required a closed circuit delivering energy to the detonator. If that energy could be diverted or neutralized, the bomb would become inert, at least temporarily. With deliberate precision, he prepared a bypass, a controlled short that would drain potential activation away from the detonator. It was a technique borrowed from electrical engineering, not ordnance disposal. Dangerous, but logical. The moment of action lasted only seconds. The insulation was breached. The wire was redirected. A new connection was made, not to the detonator, but to the bomb casing itself, grounding the circuit. The engineer held his breath, waiting for a response that did not come. No vibration, no ignition, no sound at all. Only then did he move again. The primary fuse remained untouched. The anti-handling circuit was now neutralized. What had been a trap was reduced to an inert pathway. The bomb was still lethal, but no longer unstable. Slowly, the engineer withdrew his hands. Several minutes passed before he allowed himself to shift position. He climbed the ladder without haste, emerging into daylight that felt unreal after the darkness below. Above ground, officers waited at a distance, watching for a signal that had not been promised. When the engineer raised his hand, there was no celebration, only confirmation. The bomb could now be removed safely. What had been at risk moments earlier, the town, its people, its future, remained intact. Not because of force or firepower, but because one engineer chose understanding over obedience. And as the shaft was secured and preparations began for extraction, the consequences of that choice began to ripple outward. The extraction of the bomb was methodical, almost ritualized. Engineers above ground coordinated every movement, lifting the steel cylinder carefully from its earthen cradle, placing it onto a padded sled for transport to a temporary holding site. The town remained cordoned off, though the threat that had dominated its streets for weeks had been neutralized. The air, once taut with anticipation, released slowly, though not entirely. Residents remained hesitant to return, their trust in permanence shaken by weeks of uncertainty. Official reports from the Royal Engineers and their counterparts across occupied Europe documented the operation in neutral technical language. Device rendered safe through controlled interruption of anti-handling circuitry, one summary noted. The engineer's name appeared quietly on the roster. No medal, no parade, no public announcement. Recognition for bomb disposal was measured in lives saved rather than accolades, a reality understood by every man and woman who faced a live fuse in a confined space. The number of lives preserved by this single act was difficult to quantify precisely. Civilian populations of similar towns averaged several thousand. Structural damage prevented by neutralization spared homes, churches, and schools. Public services disrupted by previous evacuation could resume immediately. Factories and rail lines once again became operational, supporting both civilian needs and the broader war effort. In the abstract metrics of military planning, the action had prevented weeks of delay and disruption. In human terms, it had preserved the familiar routines of life in a war-torn world. For the engineer, there was no moment of triumph. The work was neither glamorous nor cinematic. The streets above would fill with people again, unaware of the life and death calculus that had occurred beneath their feet. He returned to other assignments, sometimes to defuse more bombs, sometimes to repair damaged infrastructure. Each task carried the same invisible weight, a reminder that the war was fought as much in precision and patience as in firepower and maneuver. The successful neutralization of the bomb influenced operational procedures. Engineers began documenting field techniques for interrupting anti-handling circuits. Manuals were updated, slowly incorporating methods that had once been improvised. These procedural changes saved lives elsewhere, creating a ripple effect of knowledge born from one act of careful observation and controlled action. Above all, the town itself survived intact, its streets and buildings untouched by the blast that had waited silently for weeks beneath the ground. But survival carried its own burden. The population had witnessed, at least indirectly, the fragility of safety. Their return to homes was cautious, tentative. The memory of what could have happened lingered, shaping local behavior, evacuation protocols, and civil preparedness for the months and years ahead. The long-term impact of this single operation extended beyond the town it saved. Military engineers and bomb disposal units across Europe began to incorporate lessons from the incident into standard training. Previously, manuals emphasized removal and neutralization based strictly on diagrams and known fuse types. Field improvisation, once discouraged, became codified. Engineers were now taught to recognize unusual wiring patterns, anti-handling circuits, and the value of controlled intervention rather than reliance on brute force methods. The work of one careful individual had influenced doctrine on a scale that reached thousands of personnel. Bomb disposal as a profession gained a new form of respect within military and civilian circles, though recognition remained largely internal. Casualty statistics confirmed the danger. Between 1940 and 1945, British engineers alone faced hundreds of unexploded bombs, with dozens of fatalities and many more injuries. Each successful operation, like the one beneath this town, saved not only civilians but also the lives of fellow engineers, validating the procedural innovations inspired by experience. For the town itself, the incident became part of local memory, though rarely recorded in official histories. Residents returned to homes, repaired businesses, and restored the rhythms of daily life, carrying an unspoken understanding of the fine line between normalcy and catastrophe. Children played in streets once threatened by steel and explosive force. Adults walked past the site of the bomb shaft with a cautious acknowledgement of the danger that had existed just beneath their feet. On a strategic level, neutralizing unexploded bombs allowed military planners to allocate resources more efficiently. Factories reopened, railways resumed operation, and wartime production schedules, already under immense strain, could continue with minimal disruption. In other towns where bombs remained unaddressed or detonated accidentally, the human and material costs were severe, emphasizing the significance of each successful operation. The engineer himself faded from public attention. His name, unheralded, was preserved only in internal reports and quiet commendations. Yet the methodology he employed informed practices across Europe, shaping the field of bomb disposal for the remainder of the war and beyond. Anti-handling circuits became a recognized threat, and controlled rewiring and circuit interruption became standard procedures in dealing with complex devices. The innovation born from necessity had lasting consequences, both for those in the immediate theater of operations and for future generations of engineers confronting explosive hazards. Above all, the survival of the town, its people, and its infrastructure underscored a singular truth. War is not fought solely on battlefields. It is fought in moments of precision, patience, and understanding, where knowledge and calm can outweigh the destructive power of technology. The story of the engineer who rewired the bomb beneath the town is, in many ways, the story of war itself, quiet, precise, and often invisible. While headlines celebrated victories in the skies or on the battlefield, countless moments like this went unnoticed, shaping survival in ways that maps and statistics cannot capture. One life, guided by skill, observation, and judgment, altered the fate of thousands. It was not heroism in the cinematic sense. There were no cheers, no medals pinned publicly, no parades. There was only understanding, patience, and the willingness to confront danger with a mind sharpened by experience. Technologically, the episode demonstrated the evolving relationship between human ingenuity and destructive machinery. The bomb, designed to anticipate human action, was ultimately outmatched by careful study and deliberate intervention. This interplay between invention and comprehension reflects a broader truth about warfare. Machines are powerful, but knowledge and adaptability can turn their force to none. The act of rewiring, of interrupting circuits rather than applying brute force, symbolizes the quiet triumph of intellect over indiscriminate destruction. For the town, the war continued beyond the streets. Yet the survival of its homes and citizens became a testament to the unseen guardians of civilization. Engineers, technicians, and those who operated in shadows beneath the earth. History often records only battles, leaders, and movements, but here is a reminder that history is also written in meticulous hands and careful choices, where courage is measured not in aggression, but in precision and restraint. Ultimately, the narrative leaves a profound reflection. Warfare tests not only strength but understanding. It challenges humans to confront the tools of destruction with ingenuity, responsibility, and moral judgment. The engineer's hands stopped a catastrophe. His mind prevented it. And in doing so, he preserved not just a town, but a fragment of humanity itself, quiet, measured, and enduring, even in the midst of global upheaval.